random partitioning is when we understand the approximate nearest neighbors. And so let's endpoints P, Pn. We have a metric space and we want to pre-process P so as to efficiently answer queries which require finding point in P closest to query point Q in X. So epsilon approximate nearest neighbor, epsilon approximate nearest neighbor is that for any P prime, D of PQ is less than 1 plus epsilon D of P prime and Q. So the ball, let me define the ball of radius R centered at P, so this is P, this is R, is all Q in your data structure such that the distance is at most R. I have defined pleb, but let's do it again because I want to show that this connection. So this is point location in equal balls. Point location in equal balls. So given n radius balls like this, C1, I mean the center is C1, C2, C4, C5, C6. And we want to devise a data structure which for any query point Q in X does the following that I say. If there exists Ci such that Q, for example, this is Q, Q is inside a ball of radius R and center Ci. So if this is radius R, so I found a center C2. If there exists such Ci, then the algorithm returns Ci. So instead of saying a number, a binary number, because we try to partition them. So just the algorithm returns Ci. Otherwise, if you cannot find such thing, it returns no. And I need one more definition, and then we prove a theorem. So epsilon point location in equal, so it's just the epsilon deviation, epsilon pleb version of that. So now we devise this data structure such that if there exists Ci with Q, then return yes, and a point C prime of I such that Q is inside ball of C prime and 1 plus epsilon R. And if Q is not in such a ball, and you cannot find such a center Ci, for example, if Q is not in there, like this, for of course for any center, then return no. And if for the point Ci closest to Q, we have dq and Ci between R and 1 plus epsilon R, then return either yes or no. So don't care. but we return either yes or no. Why do people like Indyk and Motwani introduce such concept in 1999? Because they want to show that pleb, or more generally epsilon pleb, accordingly, can be reduced to nearest neighbor search, and of course for this can be reduced to epsilon nearest neighbor search. So it suffices to find an exact epsilon approximate nearest neighbor and then compare its distance from Q with R. So the main point to show is that there is a reduction in reverse from epsilon nearest neighbors search to epsilon pleb, with just only a small overhead in pre-processing and query costs. So essentially they are the same thing. Now let me define, if you are not familiar with LSH, local sensitive hashing, I defined again a family H, which consists of all H's, is called R1, R2, P1, P2 sensitive for D if P is in ball of Q and R1, then the probability under this hash that their hash of the points P and Q are equal is greater than P1. And if P is not in ball of Q and R2, which R2 is a bigger one, probably more than twice, then probability that hash of Q is equal to hash of P is even less than P2. And don't forget that P1 is greater than P2 and R1 is less than R2. So define a family H1, these are GP. So H1 of P, H2 of P, and HK of P and of course each of them is inside the hash family. We want to say that this algorithm exists. So let's go and say that the algorithm is this. For an integer L, we choose L functions G1 up to GL from G independently and uniformly at random. So during the pre-processing, we store each P in bucket Gj of P. So we have, for example, L buckets. Number of buckets is L. For example, for point P, we have to choose either 3, 2, 1, or 1. And in the next run, because it's a random process, it could be 1, 2, 3, 4. In the next run, it could be 2, 3, 1. 2, 4, 3, 1. So here you see that some of them are equal. So the bucket, when we say the bucket, the rows. So 1, 4, 1 is a bucket. And the number of buckets, you have for example, T number of buckets. So you should imagine something like this. Because you want to query from your data structure, and you should know how to find efficiently, because you want to reduce the order of pre-processing. Also, you want to reduce the complexity of your space. You want less space. So you're designing a data structure as a computer scientist. So now that you know the process, so in order to process a query, we search all buckets. Okay, we interrupt the search after finding first 2L points. I mean, including the duplicates. So let P1 and PT be the points encountered. So for each Pj inside the ball of Q and radius R2, we return yes and the Pj. And else we return no. So the parameters K and L, so these two parameters are chosen so as to ensure that with constant probability, first, two things holds. First, if there exists P inside, P star inside ball of Q and R1, then Gj of P star is equal to Gj of your query point. So their hash is the same for some j. And the second point is that the second property is that the total number of collisions of Q with points in anything just without the ball of Q and R2 is less than 2L, and also if you sum over all L of them, the cardinality of P minus B, Q and R2, intersection of that with Gj of Q is less than 2L. So if 1 and 2 holds, we say the algorithm is correct. So let's just prove it to see that it is a very simple fact. We are just using it in terms of mathematical terms. Otherwise, it's obvious, because you will see that. Okay, so theorem. Suppose there exists R1, R2, P1, P2 sensitive family hashing for D. Then there exists algorithm for R1. So from this you can get pleb. So there exists an algorithm for R1, R2 pleb under measure D, which uses only the n plus n to the 1 plus rho. And I will say what is rho. Space and order of n to the rho evaluation of the hash function. And this rho is just ln of 1 over P1 divided by ln of 1 over P2. So to prove this, so it suffices to hold, it suffices that the property 1 holds with probability P1 and property 2 holds with probability P2, such that both of them, P1 and P2, are strictly greater than half. I mean, it is enough to say that we prove that this holds. So both of them are greater than half. So we assume that P star is in the ball of Q and R1 if we prove this, then the proof of P star is not in the ball of Q and R2 is exactly the similar. So it's enough to prove this one. So we set K is equal to log of N with base of P2, then the probability that they are in the same hash, their hash is the same for any P inside P, but not in ball of Q and R2 is at most P2K is at most 1 over N. Because they are independent, so P2K is equal to 1. Thus, the expected number of elements from P minus Q and R2 colliding with Q under fixed Gj is at most 1. So the expected number of such collisions with any Gj is at most L, and by Markov inequality, if you have forgotten the Markov inequality, then it is just less than expectation divided by A. But now your variable is greater than 2L because I said we search 2L points, and this is less than expectation of X. I said this is just L divided by 2L. So L goes with L, and this is just 1 over 2. So the Markov property inequality, the probability that this number exceeds 2L is less than half. Therefore, the probability that property 2 holds is greater than half. Now consider the probability of Gj P star is equal to Gj of P. Clearly, it is bounded below from P1K is equal to P1 to the log of N, which is just, if you write it, it is just the same thing as I write here, log of 1 over P2, and this is N2 minus rho. Thus, the probability that such a Gj exists is at least P1. And P1 is N minus rho times to the L. So it is enough to set N to the rho to get what? P1, which is greater than and this is greater than half. So we have proof that with there exists an algorithm for R1, R2 pleb. So I just want to say, so you now know that why this variable is important, and we write it in this form, although we could simplify it more. So if rho is small, okay, so the gap between, we have a bigger gap between P1 and P2, and we have better bounds on data structure. So we have optimized the rho. Typically, rho is 1 if C is 1, and if C goes to infinity, rho of C converges to 0. You know, in 1998, for L1, the best partition is less than 1 over C plus O1. And in 2004, for L2 distance, the best partition is rho is less than C squared plus order of 1. And this is, of course, the locality sensitive hashing based on that distribution, that p-stable distribution. So we want to translate those bounds to query times. So we can say that